In the current geopolitical situation, when some crystal sources are removed from the market and supply is getting limited, it is important to increase the production yield. It represents an important shift in the production paradigm from sourcing more crystals to harvesting more out of the existing ones, from quantity to quality. My name is Ivan Orlov. I am CEO of Scientific Visual, a Swiss company that enables digital transformation in the crystal industry. We are providing tools and solutions for quality control in industrial crystals. I got my PhD in crystallography in Switzerland, and I'm heading the company for the last 10 years. In the next 12 minutes, we will demonstrate how digital quality control could help you to get extra margin and to resolve the supply bottleneck. Let's look at the semiconductor wafer production first.
So this sketch shows a typical crystal substrate production chain for the semiconductor industry. It starts with growing crystals, typically of irregular shape, followed by the extraction of cores, wafering to obtain particular diameters, thicknesses, and orientation of wafers, and other subsequent steps until embedding in the final product. For the sake of demonstration, we assume that we are talking about sapphire substrates for micro-LED displays. Today, many manufacturers evaluate substrate defects after the expensive coring and wafering steps, as the rough surface of the initial crystal does not allow defects to be located and quantified inside the raw crystal itself. At this stage, for wafer quality control, many automated systems such as Candela by KLA or Magix by Lasertec are commercially available. At this point, after wafering, a significant percentage of wafers are rejected due to the crystal defects. However, these defects were initially trapped during the crystallization process, much more upstream in the production process. But what if we could reveal these defects at an earlier production stage and adapt the next steps accordingly? For the first example, let's look at the wafering stage. So to demonstrate this, we're going to move on to a more in-depth presentation. I will explain the smart wafering approach that enables us to harvest more defect-free wafers from industrial crystals. When there are few defects in the processed core, their positioning to the cutting planes matter. Let us benefit from this effect. Knowing the precise defect coordinates allows calculating a core offset to position more defects into sawing gaps and out of future wafers. Let me illustrate the mechanism of such a gain with a simple animation. Assume we are to wafer a crystal core with a regular grid of blades or cutting wires. We set up the grid to obtain wafers of thickness T, and the wafering process will make a gap G between the wafers. The G stands for the material that will be removed at wafering. Assume our core has a few volume defects, for example, a bubble or a microcrack, which makes the corresponding wafer defective. It would be useful to put as many defects in the gap as possible so they get removed, right? So, we could slightly shift the core along the grid and see that when some defects end in the gap, we get an extra defect-free wafer. The number of defect-free wafers varies when we shift the core in the grid. Therefore, we could compute an optimal shift for each defective core that provides a maximum of defect-free wafers. How many extra wafers could we actually get, you ask? Let's check on a real crystal. This is a digital twin of a 4-inch sapphire core of 180 millimeters length. It is cored out of a large KY sapphire crystal. It needs to be wafered to 1.8 millimeter thick wafers, and the wire machine provides a 0.7 millimeter gap. It is opened in the yield software that could simulate coring and wafering. Let's start with a traditional blind wafering with no shift. We got a total of 72 wafers. Among them, 6 are defective and 66 are quality. Now let's slightly offset the core and do wafering again. The only parameter to control is the offset of the first cutting plane to the edge of the core. We got the same total, 72 wafers. Among them, 4 are defective and 68 are quality. We harvested 2 more wafers, therefore increasing the wafering yield by 3%. Now, let's opt for the smart wafering routine in the yield software. It will scan all possible wafering options and find the best one. This is the plot showing offsets versus gains. On the horizontal axis, you see the possible offset values, and on the vertical one, the number of non-defective wafers. The red point indicates the optimal shift. It is 0.7 millimeters in our case, which gets us plus 3 wafers, therefore a 4.5% increase in the yield. All that's left is to fix the core in a wafering machine and benefit. This method allows up to a double-digit increase in the wafer output without growing or buying new crystals.
Let me show you another example of applying the smart wafering. Silicon carbide is a material that is getting extremely important for semiconductor industry, for high-performance power applications, required among others for servers and telecom power supplies, solar inverters, energy storage systems, home appliances, and electrical vehicles. For making high-power electronics, silicon carbide, in the 4H polytype, they are highly doped and opaque. Here is an example of a 4-inch silicon carbide ingot that is doped with nitrogen, and we have here also a wafer that is obtained after processing such an ingot. Let me show you now how to apply the smart wafering routine to increase the yield of such ingots and get extra quality wafers such as this one.
First, we make a digital twin of the ingot, or puck, to visualize location and size of the defect. This puck is 12 mm thick and 4 inches in diameter, and it contains a significant number of defects. Traditional, meaning blind wafering, which does not take them into account, we did 17 wafers and 6 of them are non-defective ones. The smart wafering curve shows that the optimum offset for this puck is 0.55 mm. With such offset, we get the same 17 wafers, but 8 are non-defective ones. So, thanks to this optimization, we gain 2 extra wafers, therefore increasing the yield by 12%. The smart wafering can improve production by up to 2 digits compared to the blind wafering in low and medium defect ingots, and this without increasing the production capacity. The extra gain depends, of course, on the specific wafer thickness and crystal defect patterns.
At the beginning, we said that apart from smart wafering, there are other tools for optimizing production. Let's take a step forward and look at another one: smart coring. Having the digital twin of the crystal allows us to optimize the placement of the future cores to avoid defects in the crystal volume. The software helps to optimize either the total length of all defect-free cores or the total value of the cores, in case the crystal allows extraction of cores with different diameters. To avoid a sophisticated demonstration, we show here on the right a 2D animation of the optimization procedure. The video shows the inscription of cores of 3 different diameters in a round section of a defect-free crystal. In real-world optimization, the same process happens inside complex 3D shapes, and the cores will avoid crossing defects in the crystal volume. The smart coring optimization routine allows the operator to set up custom criteria for disqualifying a wafer. The minimum length of the core. Remember that the digital twin repeats the real shape of the crystal, which is usually complex, and the parameters of the coring and wafering tools. The combination of smart coring and smart wafering routines maximizes harvesting of the quality material. As an example, here you see a 260 kilogram sapphire raw crystal grown by Chiropoulos method for producing semiconductor substrates. Like a typical Chiropoulos crystal, it has a complex, non-regular shape. Its digital twin on the right side is mapped to have rectangular and round cores of different diameters. The positions of the cores avoid volume defects as much as possible. This is not the end of the possible optimizations. Alongside the rejection of defective crystals, we should take the next logical step: reducing the defectiveness of crystal growth. The objective statistics collected from the digital twins lend itself well to this. It allows us to reveal typical patterns that repeat from crystal to crystal and use them as feedback for crystal growers. An example here is a digital overlay of 1,000 unpolished sapphire ingots from the same production line. Such quality signature collects the main defects in each item and merges them into a production fingerprint. The red and blue colors indicate the morphology of the defects, while the white color marks the areas with the highest defect density. As you can see on the right, it is relatively easy to recognize the common defect patterns on such an overlay. Later, together with the process engineers, we would need to take measures to reduce them. For the sake of simplicity, we'll demonstrate here on a 2D model, but it works the same way with 3D scans. This slide summarizes gains from the ongoing digitalization of the crystal industry. Early identification of defects allows for more efficient harvesting without increasing growth capacity. Raw crystals are scanned as they enter the production line. Information on defect patterns is available throughout the production line. The green labels show the potential increase in yield at different stages of production based on our experience with customers. The exact gain will, of course, vary for each company depending on their specific production process, crystal shape, and wafering specifications. But the main framework remains the same. A digital twin is obtained as early as possible in the production process, allowing data-driven decisions to be made at later stages. So here is what is needed for smart wafering and other optimizations. The first essential prerequisite is to have a high-precision digital twin of the crystal, called a 3D scan, which includes XYZ coordinates of defects and its morphology. Once the twin is recorded, the optimization automatically goes through consecutive steps. First, smart coring, which produces optimal coordinates for core extraction, and then smart wafering, which calculates, for each core, its best offset in the wafering machine. The second essential requirement is the coring and wafering equipment must also allow to set up the offsets, while also being precise enough to implement them. So just to sum up, I underlined that the 3D defect mapping at an early stage, producing digital twins, allows a significant increase in a factory output without increasing its machining capacity. An up to double-digit increase can be achieved with the basic optimization routines. Smart wafering, increasing the number of non-defective wafers through pre-calculated core shifting in the wafering system. Smart coring, positioning the cores in the crystal to extrude into the least defective volume. Scientific Visual is a Swiss metrology company that provides automated scanners for industrial crystals. The scanners provide digital twins for raw crystals and ingots from 10 grams to 350 kilograms and enable the optimization methods we have demonstrated. Scientific Visual is proud to be at the forefront of digital quality control in the crystal industry. Our team will be happy to demonstrate how it can increase your production efficiency. Thank you for your attention. We acknowledge the support of the European Union's EIC and Marie Curie programs, which encourage European leadership in semiconductor technologies.